All right, let's dive into one of the most elegant and honestly useful data structures out there, the priority queue and the super powerful heap that makes it all tick. Let's get right into it. So picture this. Your to-do list has, 100 things on it. But you absolutely have to find the single most critical task right now. Are you really going to scan the entire list? And what happens when new, even more urgent tasks keep piling on? Well, this is the exact problem priority queues were born to solve.
So what even is this thing? At its heart, a priority queue isn't so much a specific structure as it is a promise. It's a guarantee that you can always get your hands on the highest priority item and you can do it fast. Now, for the official computer science definition, it's an abstract data type. You put items in, each with some kind of priority, and it lets you quickly find and pull out the one with the best priority. And best could mean the smallest number, the largest number, whatever you define as most important.
You know, the best analogy, hands down, is an emergency room. It doesn't matter who got there first. The person with the most critical injury is getting seen next, period. A priority queue works just like that. It makes sure the most important thing is always at the front of the line.
Okay, so the concept is cool, but how do we actually build this magic to-do list? Well, the most popular and efficient way is with a data structure called a binary heap. You can think of the heap as the engine that makes the whole priority queue concept a reality.
A binary heap is beautiful because it just follows two simple, really powerful rules. First, the shape property. It has to be a nearly complete binary tree. That just means every level is packed with nodes, except maybe the last one, and that one gets filled up from left to right. No gaps allowed. Second, the heap order property. We'll focus on a min heap, where every parent is always smaller than or equal to its children. That one rule guarantees the smallest item is always right at the top. Now, this is where it gets really slick. How do we store this tree? We don't mess with complex pointers or anything like that. We just use a plain old array. With these simple formulas, you can find any node's parent or kids just by doing some math on its index. It is incredibly efficient with space. So think about it. Because of that heap order rule, where's the most important item, the minimum value, gonna be? It's always at the root of the tree, which is just the first spot in our array, index 0. That means just taking a peek at the top priority item, it's instant, constant time.
But of course, things change. We need to add new items and remove old ones. So how does the heap keep its special properties intact? It all comes down to two clever movements, sifting up and sifting down. So to add a new item, we actually break the rules for a split second. We just stick the new element in the first open spot at the end of the array. Then we have to fix things. We sift it up by comparing it to its parent. If it's smaller, we swap. And we just keep swapping our way up the tree until the heap rules are satisfied again. And how fast is this whole process? Well, the new element only has to travel up the height of the tree. And because of that nearly complete shape, the tree's height grows logarithmically. This means the whole operation is incredibly fast. We're talking O log n time.
Removing the top item is just as clever. First, you take the root, your minimum value, and you swap it with the very last element in the heap. Then, you just pop that minimum value, which is now at the end, right off. Of course, now you've got this random element at the root messing everything up, so you sift it down, swapping it with its smallest child over and over until it settles into its correct spot.
And just like inserting, this sifting down dance only has to travel the height of the tree. So once again, the time complexity for getting the most important item out is a super efficient O log n.
And this quote really hits the nail on the head. It's the secret sauce of the heap's efficiency. Because we keep that tree shape perfectly balanced, its height grows super slowly. That's what keeps our insert and remove operations lightning fast, even if we have millions of items. Okay, so we've been adding items one by one. But what if you're handed a giant, unsorted pile of stuff and told, turn this into a heap? How long should that take? This right here is one of the most classic trip-ups in technical interviews.
Your first instinct is probably, well, if inserting one item takes log n time, then inserting n items must be n times log n, right? I mean, it makes perfect sense, but it's wrong. The amazing reality is that we can build a complete heap from scratch in linear, O of n time.
So how on earth does that work? Well, instead of inserting one by one, we use this genius bottom-up approach. We start at the end of the array and work backward, sifting each item down into its proper place. The key insight is that most of the nodes are already near the bottom of the tree. They barely have to move at all. When you actually do the math, all those little movements add up to a total amount of work that is surprisingly, beautifully linear.
And this isn't some newfangled trick, by the way. This is a classic foundational algorithm. It's a fantastic example of how a bit of clever thinking can lead to huge efficiency gains that you might not see at first glance.
Okay, theory is great, but where will you actually see this stuff? Why does any of this matter outside of a computer science class?
Turns out heaps are everywhere once you start looking. Your computer's operating system uses one to decide which program gets to run next. The famous Dijkstra's algorithm for finding the shortest path on a map uses a priority queue to figure out which location to explore next. They're also perfect for solving those top K problems, like finding the top 10 most viewed articles on a website in real time. And of course, there's the sorting algorithm named right after it, heap sort.
Now, I should mention, the binary heap we've been talking about isn't the only game in town. There are more complex versions, like binomial and Fibonacci heaps. They can be way faster for specific operations, like merging two heaps together, but they're also much more complicated. Honestly, for most day-to-day problems, the simple binary heap is your best friend.
So if you're prepping for an interview, let's just boil it down. These are the things you absolutely have to lock in. Know that the height is log n, know that build heap is O of n, and more importantly, be ready to explain why it's not O of n log n. And think about practical stuff, like how you'd efficiently decrease an item's priority, which, hint hint, usually involves a hash map to find the item quickly.
So to really wrap this all up, the magic of the heap isn't one complicated thing. It's just a few core ideas working together perfectly. That strict complete tree shape, the simple parent-child ordering rule, the fast log n operations that come from it, and that amazing counterintuitive O of n build time.
This whole structure is about one thing: efficiently finding the most or least of something in a group that's always changing. So now it's your turn. With this tool in your toolkit, what's the most important top K problem you could go out and solve right now?